Okay, welcome to the flipped classroom for AP Calculus. This begins our start of Chapter 2 with Section 2.1, the derivative as a function. You don't know it, but you've been taking the derivative of functions in Chapter 1. Formal definition of our derivative would be the limit that you've used to evaluate what we've called the slope of the tangent at a point. And that would be the limit as h approaches 0 of f of x plus h minus f of x, that whole quantity divided by h, where h is the same thing that we've been calling delta x. Informally, the derivative can be thought of as the instantaneous rate of change of a function at a certain point. In other words, it tells me how fast y is changing for a particular value of x. So if I had a graph of distance versus time, and I wanted to know how fast the distance was changing at, say, 3 seconds, I could find the derivative of that function. And that would tell me the rate of change of d with respect to time, which we would call the instantaneous velocity. A function is said to have a derivative, or to be differentiable, if all points that are in the domain of the function are in the domain of f prime of x. F prime is what stands for the derivative, and that the limit exists at these points in f of x. For example, y equals the square root of x. Well, the domain of that function is 0 inclusive to infinity. F prime of x, using our limit definition, is 1 over 2 square root of x, which is undefined at x equals 0. Therefore, we would say f of x, the original function, would not be differentiable at x equals 0 because the derivative is not defined there. Finding the derivative. We've already been finding the derivative. The expressions you get when you find the tangent is the derivative. So for f of x equals x squared, you would just take the limit as x approaches 0 of the limit of f of x plus h quantity squared minus x squared all over h, and that turns out to be just the limit of 2x, which is 2x, because remember the h's will cancel. Notations for our derivative. First derivative is noted by several different symbols. They all mean the same thing. We've already used this one, f prime of x, okay, or dy dx, which means the derivative of y with respect to x, or y prime of x. There are several others, but these seem to be the most common. Second derivative, which is just the derivative of the first derivative, is denoted by f double prime of x, or y prime of x, or d2y over dx squared. We can take the derivative of a constant function. Okay, if f of x equals some c, for example, f of x equals 5, then the derivative of that function would be 0. Because think about it, y equals 5 is a horizontal line, and the slope of a horizontal line is just 0. So the rate of change of that line with respect to x would be 0. Also, the tangent line would be horizontal, and the slope of a horizontal line would be 0. This is what you've been waiting for, the power rule for derivatives. The derivative of a function, f of x, where f of x equals x to some power n, okay, is simply n times x to the n minus 1. So you multiply by the current exponent and you drop the power of the exponent by 1. For example, f of x equals x5, x to the 5th. F prime of x would simply be 5 times x to the 4th. Okay, this rule will allow you to check your answers when you have to use the long and tedious way of finding a derivative using our limit definition. Constant multiple rule. The derivative of k times f of x, where k is a constant, is simply k times f prime of x. Here's another example. F of x equals 22.5 times x to the 5th. Well, that derivative is simply pull that constant to the outside, 22.5 times 5x to the fourth. Derivative sum rule. If h of x equals f of x plus g of x, and f of x and g of x are differentiable functions, then h prime of x is simply the derivative of f prime of x plus the derivative of g prime of x. Or not the derivative of these functions, but f prime of x plus g prime of x. Example, f of x equals 3x to the ninth plus 5x to the third. Then f prime of x would be 27x to the eighth plus 15x squared. One-sided derivatives. Okay. We say a function is differentiable on an open interval a, b if it is differentiable at every point between a and b. The same function can be thought of as being differentiable on a closed interval a, b if the derivative at the endpoints exists. But these would be one-sided derivatives. And formally, we would say the limit as h approaches 0 from the right, which equals f of a plus h minus f of a all over h, exists. We call that a right-handed derivative. And the limit as h approaches 0 from the left, f of b plus h minus f of b all over h exists, is a left-hand derivative. So all we're saying is in that interval, the derivative as you approach a from the right and the derivative as you approach b from the left have to exist for it to be differentiable on the closed interval. Example of a one-sided derivative. Let's look at the function y equals the absolute value of x. We could express this as a piecewise function where f of x equals just x when x is greater than or equal to 0, and it equals negative x when x is less than 0. Here's the graph. The rate of change as you get very close to x equals 0 from the left side is negative 1, because that line has a slope, constant slope of negative 1, while it is 1 as you get very close from the right-hand side. We could say that a one-sided derivative would exist for any interval that I choose, in this case negative 5 to 0, because that would be, as I come in from the right to 0, I come in from the left to 0, that would be a right-hand derivative, or 0, 5, as I come into 0 from the right, which we would call the left-hand derivative. I'm sorry, I had that mixed up. From 0 to 5 would be the right-hand derivative, and from negative 5 to 0 would be the left-hand derivative. We could say the derivative does not exist at x equals 0 because the two one-sided derivatives are different. This is important. In order for the derivative to be existent at a point, the two one-sided derivatives at that point, coming in from the left and coming in from the right, have to exist. Much like our limit rule, that the limit has to be the same as you come in from the left, come in from the right. However, we can have a one-sided derivative at an endpoint of an interval. Differentiability implies continuity. Sometimes people get confused with this. All functions that are differentiable are continuous, but the converse or opposite is not true. All continuous functions are not necessarily differentiable throughout their domain. Example of this we just saw, y equals absolute value of x would be an example. That function is continuous throughout its domain. However, the derivative does not exist at x equals 0. Practice problems, page 157 and 159, numbers 1 through 32. Also, something a little extra. After watching the video, I would like all students to post at least one question they had over the video on Edmodo. If you said, well, I didn't have any questions, fine. Then your task is to answer in Edmodo at least one of the questions that have been posted. See you next time. Bye-bye.